Welcome to 5.2 Notes Part 2. In this section, we're going to talk about simplifying square roots and cube roots and stuff like that using these three simple rules. So you can read this over here. An expression involving a radical with index n is in simplest form when these three conditions are met. So no radicand has a perfect nth power as a factors other than 1. Now, think about that. If you had the square root of 50, that doesn't meet that condition because we know that it has a perfect square of 25 underneath it. So, for instance, that's the same thing when we have cube roots or anything like that. So that's the first one. No perfect nth powers underneath the radicand. No radicands contain fractions, so you can't have, and we also did that. So you can't have the square root of 3/2, for instance. I'm just using the square root because it's easier to understand. Remember that we had ways of changing the square root of 3/2 and then rationalizing like this. So we did this kind of work before. Now we're just expanding it. And then the last one, no radical appears in the denominator of a fraction. Well, that kind of goes along with the second one. So because that means the same thing. The square root of 3/2 is the same as square root of 3 over the square root of 2. So there we go. Those are our three conditions. To meet the last two conditions, rationalize the denominator. This involves multiplying, like we just talked about. So here's some examples. For instance, the cube root of 135. Well, why is that in bad shape? Well, it's got a perfect radical or a perfect cube underneath the radical. You might not realize that it's a perfect cube, but we could break this down and look for this to see if there's three of the same things in 135. So for instance, I know that 5 goes into 135. Let's see how many times. Oh, it's in there 27 times, right? And if you don't know that 27 is a perfect cube, if you kept on going, you get this 9 times 3, and you get that this is 3 times 3. There's three of the same thing, which make it the cube root of 3 to the third, which is just 3. The cube root of 27, same thing. 3 on the outside and 5 on the inside. So we broke it down and we see that there's three of the same thing. I need 3 because it's cube root. If it was a fourth root, I would look for 4 of the same thing. If it was 17, I'd look for 17 of the same thing. Although I would probably tear out my hair first. All right. So in the second one, we've got a problem here because not because 7 and 8 have perfect fifths underneath the radical, but because there's a square root or there's a radical in the denominator. So before you say, well, when we did it with square roots, we just multiplied by the fifth root of 8 on the top and bottom. That's not going to do it because I need a perfect fifth in the denominator. So to think about that, I'm going to break down 8 and I'm going to see what it's made out of. The fifth root of 8 is the same as the fifth root of 2 times 2 times 2. So the question would be, how many more 2's do I need to make it a perfect fifth? Well, I've already got 3 of the same thing. I need 2 more. So if I multiply the top and bottom by the fifth root of 2 times 2, then I would have 5 2's in the denominator, and that would be the same as having 2. In the numerator, I've got the fifth root of 7 times 2, so that'd be 7 times 2 is 14, times 2 is 28. So there we go. There's the way you get the answer. So if it was the fourth root, I would need 4 2's in the denominator. If it was seventh root, I'd need 7. The point was that I was having a fifth root, and there were 3 2's already, which means I only needed 2 more. So there you go. This one over here, I need a little more room. So this one over here, 1 over 5 plus the square root of 3. We've had these before, but just as a reminder, I need to multiply by the conjugate, which is 5 minus the square root of 3 in the top and bottom. By multiplying by the conjugate, we'll get rid of all the square roots and whatever kind of roots we have in the denominator. So here we go. Let's see what that is. The numerator is easy because it's just 1 times this thing. You can put this in a box if you need to, or you can say, I know that the middle terms are going to be adding up to 0. So the first terms are 25. Square root of 3 times negative square root of 3 is 3. So it's 25 minus 3 in the denominator, or 22, because, of course, 5 radical 3 minus 5 radical 3 and positive 5 radical 3 add up to 0. Believe it or not, even though that's ugly, it's a final answer. That's called rationalized. So these are all 3 different types that you'll have. Now, To simplify addition problems, we need to have exactly the same type of root. So for instance, just like I can't add 3x plus 5y together, they're not at all the same. I can't add the square root of 2 plus the square root of 3. It doesn't make any sense because we're counting how many square roots of 2 we have. So for instance, if I add 3 square root of 2 plus 5 square root of 2, you'd be able to say, oh, there's 3 of those things and 5 of those things, which make 8 of those things. And that makes sense. But not if they're different underneath the radical. So when we have these problems here, the first one, we have one of these things and 7 more of those things, which makes 8 of those things. So 8 times the fourth root of 10. Same thing with this one. We have 2 of those things and 10 of those things, which makes 12 of those things. The things don't change, just like if you were adding 1x and 2x, you wouldn't change the x's. This, though, don't get trapped in saying this is 52 because it's not. We can't do anything with that until we see if they're really the same thing underneath. 54, let's see, is 9 times 6 and 3 times 3 times 3 times 2. I see a triplet of 2's, which means that that's the same as having a 3 on the outside and a 2 on the inside. Now I could do something about it because I have 3 of those things minus 1 of those things. 3 minus 1 is almost always 2. So 2 cube root of 2 is the final answer. But we couldn't do it here because they were not the same things to be adding or subtracting. Let's see about the last part. Try these before I do them with you. Pause the video if you haven't. Okie dokie, let's see what we got. So this one over here, I could multiply 3 times 27, but instead of multiplying, I'd rather divide this thing because I'm looking for 4 of the same things. Well, 1, 2, 3, 4 2's, that would be plus and minus. 3 is the answer because I've got a fourth root is even. So I'm going to do plus and minus 3 because there are 4 3's. Over here, a number 8, I've got, I can't have a radical over a fraction, so I could say, well, that's the same as the fifth root of 3 on the top, fifth root of 3 on the top, and the fifth root of 4 on the bottom. If I can write it, fifth root of 3 over the fifth root of, I'm not going to write 4, I'm going to write 2 times 2. How many more 2's do I need in the denominator? I need 3 more because I need 5 to get that, so it's not a fraction. These are underneath the radical, so I'll do a bunch of those. So the denominator is now 5 because I have the fifth root of 2 times 2 times 2 times 2 times 2. 2 to the fifth underneath there, that's 2 to the 5/5, which is just 2. And the numerator all get multiplied. 3 times 2, that thing, that is fifth root of 24. Oh, this one, finally an easy one. 7 of those things minus 1 of those things makes 6 of those things for number 10. And this one, these are the same things also. 4 of those things and 8 of those things, so that would be 12 of those things. Can't do much with that. These cannot be added because they are not the same things, but maybe we can break this 40 down. 40 is 8 times 5, and 8 is equal to 2 times 2 times 2. There's a 2 on the outside, so I'm going to rewrite this as the fifth root of 5 plus 2 times the fifth root of 5. Now I've got the same things. 1 of those things plus 2 of those things makes 3 of those things. And that's the final answer. I know you're thinking right now, this just can't get more fun. So let's see if we can make that happen. Oh, now they got variables. Whew. Well, actually, the variables are actually easier than the numbers themselves. So let's take a look at this. Square root of the cube root of 64, y to the 6. Well, if you break down 64, you could break it down to a lot of 2's, or if you know that 4 times 4 times 4 is 64, then you'd get 4. Now look at how easy the fractions are. If I change that to rational form, I would get 6 over 3. Well, 6 over 3 is same as y squared. In other words, I just divided the 3 into 6, and I got 2. Over here, it's the same thing. I've got the fourth root, so 4 over 4 makes 1. 8 over 2 makes 2, and you're done. See, you thought the variables were going to make it worse, and they actually are easier. Which is actually true about numbers as well. You can take a number like 64. If you said the third root of 4 to the third power, then you of course know it's 3, because 3 over 3 is 1. And I think we have one more of these. Try those. Try those, and then we'll be done with it. I think we're done with it. So pause the video and try this one. Okay, let's see what we got. Now the fifth root of 4, nothing is going to come out of that. So the eighth root, the fifth root of 8 to the 8 to 8 to the eighth, well, 5 goes into 8 one time with 3 left over. So there's 1 on the outside because that's worth 5/5. And there's 1 on the inside because that's worth 3/5. All right, same thing with a B. I got 14 of them. 14 goes into, 5 goes into 14 twice, and there are 4 left over because the one on the outside is worth 10/5, and the one on the inside is worth 4/5. And the c to the fifth on the, oh, okay, that's just c to the first on the outside. So this is a b squared c on the outside, and the fifth root of b of 4, a to the third, b to the fourth. Whew. All right, now let's see what we got here. Now 3 doesn't go into 8 perfectly, so how many more y's do I need to rationalize this thing? If it was y to the ninth, it would be good to go, right? 9 over 3 is 3. So I need one more y, one more cube root of y, so that I have y to the third in the denominator. That's 9/3, right? And what I did to the denominator, I have to do the numerator. So here we go. So x times the cube root of y over y to the third. That's supposed to say to the third power, but it's being difficult. Y to the third. And the last one, what in the world's happening here? 14 over 2, they're just numbers, right? So that's the same as 7. Now what do you have? X on the top, which is x to the first over x to the 3/4. I subtract those, and I'm going to get x to the 1/4 in the top. There's no other y's, so let's just leave the y's where they are. And that z to the negative 6, that power of a negative exponents, means that z to the negative 6 is the same as z to the positive 6 in the numerator. So there is no denominator in this problem anymore. We just have this thing as our final answer. So I think that is, oh, I guess there's 2 more. Sorry, I didn't mean to let you off too easy. If you want to try these 2, this set of pairs, go ahead, and then I'll go over them. If you are done with this, then I won't feel bad if you turn it off. All right, so let's see what we have. 5 of these things and 6 of these things is 11 of these things. All right, and this one, we can't combine these yet because they are completely different inside. But let's see if we can make them look the same. The 2 obviously is not going to change in this thing, but a 3 goes into 5 once. So I'm going to say this is the same as having 3/3 on the outside, and there would be 2 left on the inside. And this other one, 54, as we've seen a couple times, is 27 times 2. So that's the cube root of 27 is 3. So we'd have 3z on the outside and the cube root of 2z squared on the inside. So obviously if we have, now we have the same things. We have, they might not look good to you, but there we've got the third root of that thing and the third root of that thing. So it's 12 of those things minus 3 of those things. So we're going to have 9z cubed, or 9z. Is that right? Is it the 9z cubed, or is it 9? Yeah, it's 9z on the outside and the cube root of 2z squared on the inside. Here's our final answer. But we had to manipulate it before we could get them to combine. And last 2, you can try these if you want. All right, the cube root of 27 is 3. The cube root of q to the 9th is q to the 3rd. 9 divided by 3 is 3. Oh, we left the easy ones for last, huh? So 10 over 5 is x squared, and y the 5th. So 5 over 5 is 1, so it's just x squared over y.